really interesting for me personally. First couple of days we were building up many basic principles, and now we're really getting into hardcore med chem, and drug metabolism is certainly important. I had used this slide before. In order for a drug to exert pharmacological action, it has to get to the site of action. That's distribution, but after it gets to the site of action, it needs to persist long enough in the body. And the body is trying to get rid of xenobiotics and drugs. So there are enzymes in the body, particularly in the liver, that are responsible for metabolizing drugs and other biochemicals that we might ingest, deliberately or accidentally. And then you also have fecal elimination and urinary elimination that get rid of these drugs. And so that's another area that fluorine and fluorination strategies are used to perturb the properties of molecules such that they eliminate differently. So today we're going to be talking about metabolism, and there are a lot of basic properties that we'll talk about again today. In this specific lecture, we're going to be talking a lot about bond strengths and electron clouds and density. We'll talk about inductive and resonance effects and stability of intermediates. These are all really basic principles, and I was trying to prime you. On Monday, I was trying to prime you for this discussion here today on day 4. Okay, so we'll use a lot of those principles. Ultimately, we're thinking about the stability of molecules, and are they going to avoid metabolism? Much of the discussion today, it comes from a perspective article it's been reviewed once. It was resubmitted while I was here a couple days ago. And so there's a Chem Archive version that you can find. We posted a new Chem Archive, but it hasn't been approved yet, so it might come out in the next couple of days, but there will be an update to this hopefully sometime soon. But it is a submitted manuscript. So one thing I want to do right at the beginning, and I know we have first-year students, and we have some senior students here and faculty, but I want you to take about 2 minutes and look at these molecules. You have them on your pages there. And if you saw these, well, you see them now, what are the proposed metabolites that you would predict from these molecules? Okay, it might be tougher for some first-year students. Some senior students that have had more metabolism, have more experience reading journals, might have an idea of what might happen here. Okay, but take about 2 minutes and predict for me. What do you think is going to happen? We're going to see a couple of these examples throughout the talk today. These exact examples we're going to see later. There are 2 questions there. Just focus on the bold one, the first one. Okay, so you've thought about them for a bit. I'm not going to go around the room and ask for a discussion right now. We're going to see these as we go through. But I want to point out some of the substructures that you would jump out to a medicinal chemist and say that could get metabolized. So we have aromatic rings. We're going to talk about aromatic rings, how those get metabolized, and then maybe how you might use fluorine to stop those processes. A variety of aliphatic substructures. You can see a benzylic position, you can see ethers, you can see amines, basic amines that have alkyl groups attached to them. More aromatic hydrocarbon grease in that naphthyl system. Okay. So there are lots of different substructures in drugs. Metabolism can occur to CH bonds, it can occur to carbon-nitrogen bonds and carbon-oxygen bonds. You can be breaking those by unique mechanisms. And we're going to talk about how those processes go. And in order to understand why fluorine works, you have to first understand a little bit about the enzymes that promote the degradation of the drugs and the mechanisms by which those enzymes function. Okay? So let's talk a little bit about those enzymes. And first, we need to think broadly about drug metabolism. And so drug metabolism can occur by a variety of enzymes. About 50% of approved therapeutics are metabolized by a family of enzymes in the liver called CYP enzymes, cytochrome P450 enzymes. That's the blue areas over here. 50% of approved drugs get metabolized by CYP metabolism. You have some non-CYP metabolism that occurs. We'll talk a little bit about some of that, and then sometimes we just don't quite know. But it works, and it's safe, and so we can still get approval there, even if we don't understand every single thing about the drug's metabolism. We do a lot better now than we used to. Nonetheless, there are still some unknowns about how some of these drugs are getting degraded. Within this 50% grouping of CYP-mediated drug metabolism, there are individual isoforms of P450s responsible for the metabolism. In general, CYP3A4 and 2D6 are responsible for over 50% of the P450 metabolism. So there's a huge players, but there are also other CYP isoforms, 2C8, 2C9, 2C19, 1A2. There are many different isoforms responsible. And then for some of the non-CYP mediated metabolism, you have glucuronidation, sulfation, you have the cleavage of esters by carboxyesterases, monoamine oxidases are down there. Okay, so there are many types of processes that can happen. All of these processes here are these non-CYP processes. The glucuronidation is certainly a big player there. And we'll talk a little bit about glucuronidation and sulfation later on. Okay? So in general, we think about two major processes that occur, two classes of processes that occur in drug metabolism. Historically, these are called phase 1 and phase 2. There are some reasons for which we don't want to be using phase 1, phase 2 as much anymore, and instead we use oxidation phase and conjugation phase. But when you look at the literature, you might see a lot of phase 1, phase 2. Historically, oxidation is phase 1, phase 2 would be conjugation. The oxidation phase generally involves the conversion of some type of carbon-hydrogen bond or maybe an ethereal type bond, an aromatic ring, to a substructure that has a hydroxyl group or some other reactive intermediate. That increases water solubility, and it also presents a moiety that can be exploited in the conjugation phase to further promote elimination. In the conjugation phase, the body will attach some type of moiety, a glucuronide that's here, the glucuronide transferases are a class of enzymes that puts on a substructure looking like that. You can have glutathionylation reactions that react with electrophiles that will put on a moiety. These moieties are typically exploited by transport enzymes for exporting cargo out of the system. Okay. So in the liver, you have enzymes that are going to oxidize your molecule and then attach some type of moiety that then pushes the molecule out of the body. Okay. So it's, again, some people call it a two-phase system. but it's an oxidation and a conjugation series of steps that promote this reaction, okay? So that's the big picture of what's going on in drug elimination. Since 50% of drugs are metabolized through this oxidation by P450s, maybe we can talk a little bit more about that and remind everybody of some basic enzymology. So this would be the Michaelis-Menten model for enzyme kinetics. Okay, so I think it's probably taught sometime in year one. Okay, so when we think about a drug substance getting metabolized by the P450, we need to break that down into individual steps. In order for that drug to get metabolized, it needs to be recognized by the P450, and it'll go to the active site of the enzyme, and there's an equilibrium associated with this process. You have a rate forward, a dissociation rate going backwards, and those, when you have the ratio of them, we have a term Ka, that's the dissociation constant. After the drug binds the active site, then you have a catalytic process that's going to generate the metabolite. Okay, and so there are many mathematical treatments. Michaelis-Menten is one popular one that's used. And so when we see the discussions of drug metabolism in the literature, most of the discussion focuses on what's happening in this catalytic step, the oxidation step itself. There's very little literature discussing how the drug association occurs. But you can make substitutions to the drug such that it no longer binds well to the P450s. It's under-discussed, and that's kind of the point of my perspective, is we need to be paying more attention to the association, because we know fluorine can perturb the association of molecules, and we study that in a little bit more depth tomorrow. So, the metabolite, after it gets oxidized, can then react with subsequent enzymes and or glutathione that make the conjugates that ultimately get eliminated. Okay. And the argument here is that, yes, fluorination can definitely perturb K-cat, but we also need to be thinking about how fluorination might perturb the association or the recognition. Okay. And there's very, very, very little discussion and very little data for this process here, and I think there's a gap for people studying in that space. So we're going to talk a little bit more in depth about the oxidation phase and those P450s. For those individuals that aren't aware of the P450 system, I can provide just a little bit of a background here. So P450 enzymes, it's a class of enzymes for which there are many isoforms. They are localized in the endoplasmic reticulum. They have a protein structure with a tail, lipophilic tail, that embeds and forces that enzyme to stay in the membrane. So when a greasy drug, a lipophilic drug gets metabolized, that greasy drug will exist in the membrane. Like a lot of them are lipophilic. So they're okay being in the membrane. They'll get into the water, but they'll go back in the membrane, right? We were talking about the transition back and forth across membranes. So some of the greasier drugs will be sitting in the membrane, and when they're in the membrane in the ER, the substrates can kind of get uptaken into the active site of the P450 where they're metabolized, and then ultimately they get released as the metabolite after metabolism. So it really is the greasiness of the drug in many cases that helps get in here to start. Okay? So you can kind of see that again over here in this slide. You have the enzyme. It gets really attached through a series of amino acids with greasy moieties presented there. So you have a hydrophilic area that attaches the P450 to the membrane, and then a more water-soluble side over here. In the active site of the P450, you have a heme. Okay, and the heme structure is kind of embedded there. That heme has an iron in the middle of it, and that iron is going to be the catalytic species that reacts with oxygen, gets activated, and does all the key bioinorganic transformations that we're going to talk about. Okay? So that heme does require an NADPH reductase to help the cycle, promote the cycle and regenerate the active species. That NADPH reductase requires NAD, right? So you also have a co-cycle going on in the background. I'm not going to talk about it in depth, but you do need to be thinking about regenerating the active species using another enzyme. So there are many isoforms, and the main isoforms for drug metabolism are shown here. You can see the representative contributions to drug metabolism here out of a series of about 800, 900 drugs that were established. There's a huge variance in the active sites of these enzymes. Some of them are pretty small and linear, some of them are a little bit more round and bigger in space. Some have like little L-shaped bends in the active site, so they'd recognize molecules with different shapes. Some of them are more hydrophobic, and so they love greasy molecules. Some of them will have charged anionic residues right above the heme, so they attract cationic amines. When I'm talking about cationic amines, we've already been talking about modulating amine pKa with fluorine. So I'm trying to give you a hint about what we might be seeing a little bit further downstream. Okay. So that's in the substrate binding residues. Again, some of them are more cationic, some of them are anionic, some of them are just really greasy and recognized grease. And the representative substrates, you might recognize some of the names of some of those drugs. We never know in advance when we build a drug, like which P450 is going to be responsible. And sometimes when you optimize to try to avoid metabolism by one P450, maybe another one kicks in that you didn't expect. And so in order to do drug discovery properly, when we measure the metabolism in vitro, we'll use pooled microsomes. Pooled microsomes are like the ER. You separate the ER from the rest of the cell. That ER has the P450s in them, and then you kind of have a time course study where you subject drug to the microsome. It has the P450s in it, but it has a bunch of P450s. It doesn't have one isoform. It usually has all the isoforms there. So it's tough to study which isoform is responsible, and it takes a lot of follow-up studies to figure out which one is responsible for metabolizing your drug. Okay? So the catalytic cycle is shown here. In this case, we're using a generic organic substrate that really doesn't have a structure. But this overall process that occurs at the metal, at the heme, occurs regardless of the substrate and regardless of what mechanism is going on the organic molecule later on. So we're going to look at 3 different mechanisms later on in terms of what's going on the organic molecule, but all of them have this type of cycle for the heme. So the heme is going to have a resting state in which it's hydrated, so there's a water bound to the heme. The substrate can move into the active site of the enzyme, and water gets displaced in this process. After this, there's a reduction of the iron, and now it's in a prime oxidation state to react with oxygen. The oxygen itself, upon binding, has a 1 electron transfer, so you get back to a higher oxidation state iron. Again, another reduction occurs, and you can see the reduction here, and now we have an active species. Upon protonation, we get to a peroxide. Here's our active species. This species is what we call compound 1 in the literature. This is the key player. This is the high oxidation state species that reacts with your organic molecule. So this one right here, 16. Okay. Through a variety of processes, this iron oxo will then oxidize your molecule. There are 3 mechanisms that we'll kind of look at: arene oxidation, aliphatic oxidation, and then dealkylation reactions. We have an NC or an OC bond that gets cleaved. Okay? So there are multiple different things that can happen here, but all of them will oxidize your substrate. Eventually, replacement of the substrate, oxidized substrate with water, gets you back to the resting state. Okay? So the details of that are, in my mind, important to know the big picture of what's going on, but more critically for metabolism, you want to have a fantastic idea of what's going on there, and that's where we're going to spend a bit more time. So we're going to start with arene epoxidation. You find aromatic rings all over drugs, and fluorine is well known to help modulate the properties there. So the mechanism of what's going on in this case is shown here. In general, this is the active species, that compound 1 that I had mentioned before. I'm going to be using this term. But remember, it's that iron with a double bond to oxygen there. And then the heme and the whole enzyme is there. But as an organic chemist, an organic metallic chemist, I can pretend like the rest of the enzyme isn't there and think about the metal and the redox chemistry going on at the metal as being like a just really simple iron oxo species. Okay, so we can simplify for purposes of the discussion here. So the arene itself undergoes electrophilic attack. So the iron oxide is electrophilic. You can see the charge on that species. The pi electrons will attack, generate this type of cationic intermediate here. And then there are two pathways that can occur after this step. In one pathway that's commonly used to rationalize the metabolism, you can reform a second bond between the oxygen and the cation, and that gives you an epoxide or an arene oxide. And that arene oxide can undergo an NIH shift. That NIH shift involves the movement of electrons from one of the CO bonds to the other to make a double bond. You can't have 5 bonds on carbon, so you'll have a hydride shift. H minus will shift back over to the other position. That generates a ketone type intermediate, which spontaneously, rapidly tautomerizes to a phenol. So we see the phenol metabolite. It looks like we've replaced a CH with a CO, but the mechanism is not a CH activation, CH insertion. The mechanism requires different steps. In a second mechanism that also occurs for some substrates, you can have an NIH shift directly from this cationic intermediate. So from the iron-oxygen bond, if you think about those electrons as forming a CO double bond, and then the hydride shift quenching the carbocation, you get to the same intermediate that ultimately tautomerizes. Okay. So those are two different mechanisms that get you to the same product, and there's evidence in the literature for some substrates you go through one process, for other substrates you go through the other process. A key point to remember in this mechanism is that the pi system of the arene is nucleophilic. The pi system attacks the electrophilic iron oxo. It's not the CH bond. It's not a CH bond insertion. Okay. And as such, we should be thinking critically about the pi density and substituents on the ring that increase pi density might accelerate this process. Substituents on the ring that decrease pi density might decrease the rate of this process. But CH bond strength is not the key driver here. You don't do anything with CH bonds until you get to later steps in the process. Okay? So keep that in mind. Then we'll start to think about how different substituents, including fluorinated substituents, perturb pi density, and then how does that relate to drug metabolism. So these are some calculations that my group did, still unpublished, but submitted for publication. Is that a military plane? That's a different engine, different type of engine, sounds like. Okay, so as a benchmark for these, we're going to be using benzene as a benchmark, and we have a couple of other comparators built into here. For benzene, we have HOMO energies, and then you can see the diagram here. Red means there's more electron density. The greens and the blues mean less and less, less electron density. So benzene, you have that pi system that's above and below the ring. You see a nice red character there. If we go over to chlorobenzene and fluorobenzene, you see slight perturbations there, maybe not quite as pi-rich. The HOMO energies here actually get slightly less, yeah. And so that's kind of important. You get higher energy there, positive trend. So you actually accelerate metabolism because the HOMO energy is a little bit higher there. It's more nucleophilic, higher HOMO energy. Remember, these are negative values, right? So you have to kind of recalibrate yourself. These are negative values. Okay. So when you get to difluorination, here we have 1,2-difluorobenzene, 1,3-difluorobenzene. We see the HOMO energies still being pretty close, not a great perturbation in the HOMO energies, So those catalytic processes for these simple model systems are anticipated to be very similar. When you start to get down to trifluorinated substructures, 1,2,3, 1,2,4, 1,3,5 trifluorobenzene, that's where you start to see a little bit more of a notable decrease in the HOMO values. You see more of a green color in there. And now we're thinking that maybe we're decreasing electron density sufficiently to perturb metabolism. So don't always expect a huge benefit from monofluorination. Sometimes it works, many times it won't. Difluorination, you had a little bit better chance. If you're really trying to drive that HOMO energy down, you need 3 fluorines in there to have a significant likelihood of success. Okay. So we're going to look at another series of compounds. We're going to start with toluene and look at CF3 derivatives. So you can see the toluene energy is there relative to benzene, 0.34, but that 6.14 is what you want to keep in mind. You lower the HOMO energy pretty drastically when you put 1 fluoro, 2 fluoro, 3 fluoros on that methyl group. So now we have trifluoromethylbenzene, right? Fluoromethyl, difluoromethyl, trifluoromethylbenzene. Our HOMO energy value has gone down pretty substantially. You can still see a lot of the yellow and the green character there. If you have bis trifluoromethyl substructures, that HOMO energy drives down quite a bit more. So now we think about a less and less and less nucleophilic pi system. There's another one, and then there's another 1,4 bis trifluoromethylbenzene. And then just for comparison with some other functional groups that you might see in drug discovery, we've done some calculations. You have anisole that increases the HOMO there. Difluoromethoxybenzene, trifluoromethoxybenzene, those are how you would take an anisole and reduce electron density. Again, lower that HOMO. And so this is another nice series that might be valuable to think about for your own campaigns. Nitrobenzene, powerful electron withdrawing group, lowers the HOMO to minus 0.76. Benzonitrile, another electron withdrawing group you'll see in a lot of drugs. We're going to talk about this substructure in one of the key examples when we move forward. Anilines and phenols are considered to be really redox active. They're not always the most stable substructures in drug discovery. And those are easy to oxidize. Pyridines, incorporated into many therapeutics, lower the HOMO energy. They're less nucleophilic than benzene. The calculations support that, and we are going to use this one in some of the structures also, in some of the discussions. And then indole, electron-rich heterocycles, raise it back up. Okay, so this is intended just to get you thinking about the pi density more than anything. The quantitative values I don't expect you to be applying here right now in class, but they are documented in there. So let's go ahead and start talking about examples now. I've kind of laid the basis. These 2 examples, the one on the left is the one we're about to cover, and that's one of the ones I asked you to look at right at the beginning of class. Okay, so let's look at that one. That's a precursor to a compound that made it into phase 3 clinical trials and failed because it had some other adverse effects that weren't desirable. So in this series, the parent compound, and the one you looked at before, is a compound for which this was a hydrogen atom, and over here you just had a phenyl ether. And this compound it underwent metabolism. Metabolism occurred in microsomes, and the working mechanism and the speculated mechanism is that it underwent arene epoxidation, and then the arene oxide reacted with glutathione to make adducts that look like this. And they could detect those glutathione adducts. And then a second thing that they could detect, when you have these arene oxides, they can also react with nucleophilic residues on the microsomes. And so you can detect adducts that have the drug bound to the microsome and quantify those. Okay, so that's the covalent binding to liver microsomes that they're talking about right here. So that's what's going on with the data. The parent compound itself is a 2 nanomolar inhibitor, antagonist of a cannabinoid receptor. The Formation of both the glutathione adducts and the human liver microsome adducts was detected in high quantities. In order to reduce metabolism, the group needed to have less nucleophilic pi systems. They focused on the electron-rich phenolic ring. Phenol, this one's a phenol. This is an electron-rich ring. This one is neutral when it's just the phenol, right? So this one's likely going to be more active. And in the next series of entries that I'm presenting here, there are many others, but I'm just presenting, the team tried a couple of different substitutions. The 3,5-difluoro was a potent compound, maybe a slight reduction in the covalent adducts, but not enough to push the program forward. The pyridyl substitution that I had mentioned a slide ago was used, and that further reduced the covalent adducts that were being observed in this case. That wasn't enough. They need to keep reducing electron density. You're still seeing some of those adducts form, so let's continue to introduce more and more and more electron withdrawing groups. So the chloro and the CF3, both sigma withdrawing groups, inductive withdrawing groups were used here. You can see the 5-chloro, the 5-trifluoromethyl, still potent compounds, fewer and fewer of those adducts being formed. At this point, the metabolism of the aryl ether system was negated. And in drug metabolism, if you completely block one moiety, it's common that an alternate moiety in the system gets metabolized by a different P450 enzyme. And that's where they started to observe oxidation of the neutral ring over here. Now this is the most electron-rich system. After they blocked this one, metabolism starts occurring over here, so now we have to solve that problem. In order to solve that problem, same general strategy, let's make a series of analogs that have less and less electron density over here on this system. Ultimately, the combination of the 2-pyridyl 5-trifluoromethyl, aryl ether over here, with an electron withdrawing nitrile, suppressed formation of the covalent adducts and ultimately delivered the clinical candidate that made it to phase 3. Okay. So a lot going on here, but it's a great story where on 2 different ring systems, they're having to reduce electron density ultimately to reduce the metabolism. Okay. So in a second example that we'll talk about, this is the development of gefitinib, an EGFR inhibitor that is approved for cancers. An early lead compound has this substructure here, the 4-amino-quinazoline substructure with 2 ethers, screams out EGFR, like this ring system over here. You see enough of these drugs that's common. It's a pharmacophore in many of them. The early fragment-sized compound had this aniline with a methyl group on it, and that was determined to undergo metabolism. Of course, a lot of these compounds go through metabolism. That's why it's a metabolism lecture, right? So it underwent metabolism to make 2 different, metabolized predominantly. You can see aromatic hydroxylation occurring over here, benzylic hydroxylation occurring over there. We'll talk about benzylic hydroxylation in a different part of the lecture. So in order to further develop this compound, you want to think about removing electron density from the aniline ring system, because that's the electron-rich system. Many analogs were made. Another important derivative in this series was the chloro-fluoro derivative that extended the half-life of the compound from 1 hour to 3 compounds in vivo. This is in vivo PK data here. And then with the extended half-life, further medchem optimization, changing the substituents here, delivered the clinical candidate and ultimately approved compound. I'll say there's a typo here. That should be OME that I'm just seeing right now. Okay, so that should be a methyl ether. So that's the drug. Key point here is that we're removing electron density from this system that has an aniline donating in and a methyl group donating in. And we did some calculations to estimate what the homos of those fragments might look like, what type of pi density is in those systems, and the starting point, the toluidine right here is shown there. You can see how red that is from the donation of both moieties. You can attenuate the pi density, reduce the pi density, attenuate the metabolism with the chlorofluoro that both pull electron density out through sigma withdrawing effects. Okay. So that's a story there. Main point, when you're thinking about the metabolism of aero rings, think about the pi density. You can do these types of calculations pretty quick, or just look at linear free energy relationship parameters and you get a feel for electron-rich and deficient systems there. Your intuition and arrow pushing is also fantastic as a first attempt at any of this. So let's talk about aliphatic. Oh, maybe I should pause there and just see if there's any questions first. Any students back? More senior students in front? Super senior students all the way in front?
Yeah, I have one question. This SIP-mediated metabolism.
This what metabolism?
SIP-mediated metabolism. So in one of the slides, there was a metabolism happening, like oxidation happening in one ring, and which was a nickel ring, and then it was blocked, and then it was happening in another ring. So how SIP is actually accommodating, because that is again a receptor and ligand kind of interaction. So how come so SIP has a very flexible kind of thing where it can accommodate?
Yeah, some SIPs are more flexible than others. And remember, there's a family of enzymes. It's not one enzyme, right? So some of them are going to recognize a lot of just grease. Some of them will be looking for a basic amine or a methyl ether, just because they have active sites that have, amino acids dangling out right above the iron that recognize certain moieties. Okay. So, it's really tough to solve it when you just think about one enzyme alone. You kind of look for trends of things that can happen in general to a drug, and then how do you stop that regardless of which P450 is responsible? Yeah, it's really tough. Okay, so we have this example here. We're going to move on to aliphatic oxidation, and this is the sub-story that you're going to want to pay attention to because of the other discussions with the aliphatic tail sticking off the heterocycle. Okay, so this is going to be directly relevant. So I'll find a good stopping point in about 20 minutes for the transition. So in this type of process, there's a different mechanism. We're talking about aliphatic CH bonds. Here we have an aliphatic CH bond. The reaction that occurs is actually an H atom abstraction, HAT. So the iron oxo will rip off H dot and reveal a radical. And then through a radical rebound process, the hydroxyl group, this first step here, when this rips off H dot, it makes this iron hydroxyl. And through a radical rebound process, we'll have one electron come from the hydroxyl, make a bond with this single electron there, and that's how we get the alcohol. Different process. This one does involve direct cleavage of the CH bond in the rate limiting step. The other one didn't. The other one had that pi system reacting. This one does involve a reaction of the CH bond. So different mechanism, different rules. We can use fluorine and fluorinated substituents to replace the CH bond with the CF bond. The CF bond, it's not going to cleave by a P450. Okay, there are two reasons. One that's cited over and over and over in the literature, and I don't think it's the better reason, but let's go ahead and look at it. It's true. The difference in CH versus CF bonds is different, so you get about a 9 kcal/mol increase in energy for a CF bond relative to a CH. Okay, that's fine, that's fair, that's true, that's good. The CH bond is certainly stronger, sorry, the CF bond is certainly stronger than the CH bond. But if you do a deeper just analysis and think about what's going on at the metal, not just looking at the ground state of the starting material, you actually get ridiculous intermediates that would form if you try to abstract the F atom using an iron oxo. So if you try to replicate this initial step with a CF bond, you would make a radical, sure, that's fine, but look at that intermediate there, OF, pretty weak bond, right? Oxygen, fluorine, both electronegative. that's not a stable species. That might actually be explosive, and we don't want cells exploding, right? So, and we did a quick energy analysis of this. So this is just a little cartoon here that shows the process if you abstract a CH bond, that's down here, and then the one that abstracts an F bond, a fluorine atom, would be shown here. There's actually a 55 kcal per mole energy difference here, so I know why while people like looking at that 9 kcal per mole difference and say, yeah, that's why it doesn't happen, I think you might also consider the energies here. And the OF versus the OH bond strength are pretty drastically different. And maybe that's a reason too. You don't have an iron oxo, the oxygen presenting towards a fluorine atom, that's going to be disfavored in the transition state that precedes this step. So that's a bad interaction right there. So just a different analysis of the same phenomenon. So that's if you replace the CH that's metabolized by a CF, but we should also be thinking about other hydrogen atoms in the direct vicinity. Okay, so if we have a methyl group and we replace one of those methyl groups, one of the CH bonds with a CF bond, how is that going to perturb the metabolism of the substructure? This is a series of model substrates. We'll look at it over a series of animations here. Your slides are just the slides that are all black, but hopefully my coloring helps walk through a lot of data more effectively. So, in the first example here, we're going to look at fluoromethane and methane. You can see fluorination actually decreases the BDE. So we put a fluorine atom in there and we make a weaker CH bond that'd be more easy to cleave by the P450. Okay, so we actually see a decrease in energy there. That's not exactly what we were looking for, but let's think about the electronic structure of the radical, and is that radical more or less stable? So when we abstract H dot from fluoromethane, we would get to the CF2H that has a single electron on carbon. Fluorine still has a lone pair of electrons, and we can get orbital mixing. In that orbital mixing diagram, we make a pi bond that involves one electron from the carbon with one electron from the fluorine pairing. The other unpaired electron from fluorine goes into the pi star, but we have two electrons going down, one up. It's ultimately a stabilizing substitution. Okay, that's why you see the weaker BDE. It's easier, it's more facile to abstract this hydrogen atom, alpha, to a fluorine atom. You have monofluorination. Now that contrasts what we would normally think about, and that we normally think about the sigma withdrawing effect. And the sigma withdrawing effect suggests that the BDE strength should be higher. So we have competing effects here. We have a hyperconjugative effect that's stabilizing. We have the electron withdrawing nature of the fluorine destabilizing that intermediate. With one fluorine atom, with two fluorine atoms, the hyperconjugative effect wins. But when we put on the second fluorine atom, so here we have CF2H, we get a little bit stronger relative to the monofluoro, but still ultimately a weaker CH bond than the methyl itself. When we put on the third fluorine atom, that's where we start to see the inductive effect outcompeting the hyperconjugative effect, and so that's where we actually see an increase in the bond association energy. Okay, so you have these competing effects that we need to think about over here. And again, these are some of the effects we were talking about in day one. I said they're going to become relevant as we move forward. So that is all alpha fluorination. That's all if the CH bond that you're abstracting is directly attached to a fluorine atom. But we can also fluorinate vicinally. We can keep moving the fluorine out one position, another position. So let's ask the question about what happens there in those systems. And I'll say that this system here, this is still alpha fluorination. So you see the same trend we just saw in the previous slide. We are substituting alpha with one fluorine or two fluorine atoms, and again, they're weakening the BDE. Okay, so now let's go to the system that I was talking about. If you fluorinate vicinally or beta fluorination, And in this case, everything is going to destabilize the radical. Okay. So let's look at this comparison. Here we have ethane relative to fluoroethane, difluoroethane, and trifluoroethane, but we're thinking about abstracting the CH bond that is not connected to the CFs. The benchmark number that you should have in mind for comparison is 100 kcal per mole here. We've reset our 0 point right there for the rest of these calculations. The introduction of one fluorine atom increases the bond association energy. Second fluorine atom increased. Third fluorine atom, CF3, also increases. And so in this case, we're just thinking about the sigma inductive effect. You have a radical, it's electron deficient, not perfectly happy. The presence of fluorine atoms removes electron density or pulls electron density away from a species that is already electron deficient, and that's not a favorable interaction there. Okay. That's where you see the increase in bond association energies if you fluorinate beta. So the situation is a little bit tricky. If you have alpha fluorination, like the ones we discussed here, over here you have no hyperconjugative effects, you're only thinking about the inductive effect. Then we see the increase in bond association energies. So this strategy can be used in many different ways and has been used in many different ways. Fluorination of aliphatic systems can block metabolism or at least perturb metabolism. This is a steroid. You can see the ABCD ring system. This is a fungal species that can be used to estimate metabolism. Fungi are eukaryotic, so they have P450 systems that are pseudo-similar to mammalian systems. Okay, they're not prokaryotic, they're eukaryotic fungi. And so this is a model that's used occasionally. It's a slow model. It takes a while for these to go. Nonetheless, you can get some studies done with these types of models. So with this fungal species, they'll metabolize the steroid. They'll put hydroxyl groups on the C and the D rings there. If we want to block metabolism here of the C ring, you can put fluorinated substituents there, and that effectively blocks metabolism at this position. Now, as we saw in the tranabant example, that cannabinoid example, you block one position, maybe a secondary position that you didn't expect pops up and starts being problematic, so that's what happens in this case. When you block this position, now you start getting a new hydroxylation at the B ring occurring. Okay, so that's important to think about. Another important lesson or thought, we talked about fluorination of the site that you're trying to block, or vicinal fluorination. So if we fluorinate one position over, we can still destabilize the radical intermediate. And that's what's going on down here in this example. Okay. The species tends to hydroxylate this position right here. But we can block that position by putting fluorine adjacent. We shut off metabolism at that site, that whole ring. Don't see any metabolism there. Okay. Now you still have the primary site that gets metabolized, and the metabolism does shift over here, so you still get B ring hydroxylation. But we have effectively, for teaching purposes, we have effectively blocked metabolism of this ring by introducing fluorine at the adjacent site to the one that gets hydroxylated. Okay. So teaching point there. Finally, we can introduce fluorine to other positions. This one isn't very good necessarily for teaching purposes, but if you put fluorine down over here, you still get the initial hydroxylations that you would get anyway. So it's just a nice benchmark, a nice comparator to have to include here. Okay. So hopefully you saw that the strategy in action has been used in more complex settings. So this is an FDA-approved drug development sub-story shown here. So this is a NS3A inhibitor, an antiviral, anti-hepatitis C drug. The structure is crazy. I mean, that thing's a monster, right? And there's probably 6 or 7 drugs in this class that have similar structures to this approved now. In this lead series, reasonably optimized series, you have a vinyl group here. You can have this heterobenzylic ring system. Both of them underwent metabolism. So the aliphatic system was metabolized here at the benzylic position. Benzylic positions are notorious for getting metabolized because when you make the initial radical, it's benzylic, it's stable, because the resonance structures that you can draw are where the radical distributes into the arrow ring. So the benzylic positions are extremely susceptible to metabolism. The second process that occurred was over here on the vinyl group, and that made an arene oxide the way you would see in the first step of this made an epoxide similar to the arene oxide you saw in the aromatic case, right? In the aromatic reaction you studied, they made an epoxide. It's on an arrow ring. This is just a vinyl group. It's CYP3A4 that did that. Now, this is an electrophile, so it can react with nucleophilic cofactors, and glutathione opens this up, and then this was detected, the glutathione adduct. So we have to solve those two problems, and here's a series of examples, series of compounds that were prepared in order to further progress the project, improve potency, and also improve the metabolic properties. So I have this other substructure over here in which we're looking at R1, R2, R3, just to keep people calibrated with the positions I'm trying to focus on. I put that over there. So you could optimize some of the other aliphatic groups here, R3 and R2. You can see those. You can have H, you can have methyl, methyl ethyl. They're small, so the pockets here, you don't want to grow them too big. Nonetheless, the metabolism was not occurring at those sites, so we kind of let them be, let the SAR that drives the potency really control the decisions here. The smaller substituents seem to work well. The clearance is important here. That was a weird noise. Okay. So the metabolism is shown here. These are reasonably high numbers. We want to get these numbers down to those that you see down here. Okay. In order to address the metabolic issue over here at this vinyl position, that would be R1, there were some attempts to change the pi bond to just an aliphatic system there. You're still seeing some metabolism at that site. That was still occurring. So in order to block the metabolism at that site, a fluorination strategy was employed. So here you can see a series of fluoromethyl and fluoroethyl derivatives, reasonably potent compounds, some of them, and a decrease in the clearance in hepatocytes. So that was a good success story. You have not yet addressed the metabolism occurring over here at the benzylic position, but the fluoroalkyl substitutions here did benefit the metabolic, or avoid the metabolism down here on what was a vinyl group. Ultimately, a combination of fluorination strategies was used in this case. So you still have the CF2 group over here, the monofluoro and difluorinated substructures were introduced here, and you can see a decrease of the metabolism and shutting that down pretty significantly with the difluoro. Really nice potent compound. This ultimately became an approved drug. So fluorination at different sites became relevant here. In one case, we're dealing with the benzylic fluorination. In the other case, this was an interesting group. You don't see many vinyl groups in drugs, predominantly because they can get oxidized, make an arene oxide. And this was a nice strategy used here to stop that. Okay. So I'll pause after a couple of stories. How are we doing? Good? Okay, I'm going to work through another series. I'm going to introduce a couple of slides, and then there are several slides of data that you can read through on your own. But I'm going to talk through the general principles and walk through a couple of the slides, and then the rest are just like an attachment for you to look at on your own. So I want to introduce a concept called vicinal difluorination. We've seen the CF2 group all the time, right? You see it in a lot of different drug discovery campaigns. It turns out that vicinal difluorination can introduce distinct properties relative to geminal difluorination. The reason why is shown here. When you think about the dipole introduced by each fluorine atom, the overall perturbation and properties will be the result of the sum of those vectors. Okay, so if the net vector is greater, you're going to see a bigger perturbation and properties. When you have geminal difluorination, you have two vectors that are at 90 degrees from each, tetrahedral, yeah, from each other. And so the sum of the vectors, part of them cancel each other out, so the net sum is smaller than if you have vicinal difluorination. If you have vicinal difluorination, the sum of the vectors is going to be greater there. And that further modulates properties. You can see the summary is right here. So when you think about the changes in lipophilicity, geminal difluorination typically makes things greasier than vicinal difluorination. So if you're trying to drive water solubility, you can do it better with this type of substitution. And so that's what's shown here. Vicinal difluorination is shown there. So log P and solubility in water, they work against each other. In terms of metabolic stability, the vicinal difluoro seems to be more stable in a series of model systems also. So again, pretty important for some campaigns that might have long aliphatic systems attached to a ring. And so I can show you a little bit of data to support that.
Then the vicinal one, the log P is actually okay. That means the geminal. This one is more hydrophobic in nature.
This one will be more lipophilic
so this will
than
bind
this.
Bind also in the enzyme maybe in a better fashion. So that is the reason it will get hit. Yeah, that's right.
This is a little bit greasier than that is.
So that will bind also to the enzymes in a better fashion.
For P450s that just look for grease,
Yes.
this is more likely to engage those ones than this substitution pattern. So here's a series of compounds. You can see the changes in lipophilicity. Maybe just to benchmark everybody, here's the aliphatic system. If you put like a fluorine atom or CF2 group, again, you drive water solubility a little bit because we talked about this on day one. Day two. No, yesterday. Yesterday was solubility, right? So slide one yesterday. We talked about this, how if you start fluorinating aliphatic, you increase water solubility. Okay? And you see that here. The log P, as you put a couple of fluorine atoms, gets more water soluble. Okay? Decrease in log P. The key comparator for this discussion, there are a couple of them, maybe this compound versus this one, and this one versus this one. You can see these ones are less lipophilic. This one, the vicinal difluorination, than these ones over here. And you can see it in some other systems too. I have quite a bit of data. The second important correlation here is to show the correlation between lipophilicity and metabolism. And you can see the correlation. We try to lay these out. So you can see the correlation that goes up and right. As things are greasier, they tend to get metabolized more quickly. As things become more water soluble, the metabolism does shut off a bit. Okay. And the same is true in other systems. These are systems for which you had an ether linkage between your heterocycle and the aliphatic system. Okay, these are systems that are similar. You just don't have the ether. So this is just the alkyl group coming off the heterocycle. And again, this is where we start thinking about, your substructures that you're thinking about. Okay, so you can, with this vicinal difluorination, you can decrease lipophilicity overall. And you can pattern these fluorine atoms in a variety of different manners. And you can think about the stereochemistry. Maybe you can influence potency or selectivity for your target by having stereo centers over here on your molecule. Maybe you don't want to worry about that, but it's up to you. But in general, the vicinal difluorination is a greasier substitution. The CF3 is a greasier substitution than some of these other ones that are vicinally substituted. And so again, more data. There's more data in these. This is water solubility here. So now we're looking at log P versus water solubility. You see the inverse correlation, so the less lipophilic ones. But look at that. Look how much. Look how soluble that is. That's crazy, isn't it? Yeah. Okay. And then the clearance there. So let's look at a couple of examples right before the break. This is that fungal model again. We saw the patterning of these cyclohexanes in a previous lecture. And so here they're coming up again in the metabolism. In an example here, we see metabolism of the aliphatic system at several different positions. Around the aliphatic ring, you see some of the benzylic position that gets metabolized too. 100% conversion. If we put another fluorine atom, we decrease the metabolism, we still see benzylic fluorination there. You can see the decrease in log P, and if we put another fluorine atom in there, we're, again, a little bit less lipophilic, a little bit more stable, less metabolism occurring in this system. So you can use multiple fluorine substitutions to drive metabolism. So, yeah. I'm going to pause. That's the end of this subsection. Any questions before we break real quick? People ready for tea? Okay, so we'll get some tea and we're going to come back. What time do you want to start the next one? It's 11:17? Yeah.
Yeah, we'll take a 15-minute break. 15 minutes break, then we will edit that.
Okay, 15 minutes, cool.